Okay, today we are entering a new module. This is module 5 and it deals with the solution of linear algebraic equations. We have seen that as part of the CFD solution we take the partial differential equations which govern the flow and we use finite difference or finite volume or even finite element methods or other methods to convert these into a system of algebraic equations. And we have seen that, for example, in the course of solution of compressible flow or incompressible flows, we often end up with a system of linearized algebraic equations, and we'd like to focus on how to solve these things properly and efficiently. In the first lecture that we're going to have, we're going to look at the motivation for us to seek some special methods for the solution of these, which is at the heart of the CFD, the CFD approach. So we'll start with a brief recap on the discretization of the governing equations. We know that we have a governing equation which is of this form: dou by dou t of rho phi plus del dot rho u phi equal to del dot gamma delta gradient phi plus s phi. This is a time dependent term, this is the advective flux of phi, this is the diffusive flux of phi, and this is source term. And we have seen that this equation with different source terms and different diffusivities and different velocities leading to convection can, and different values of phi here, can represent all the basic equations like the mass conservation equation, momentum conservation equation in each directions, the energy conservation equation, the species balance equations. All those equations that we wish to solve are of this particular form. And if you take the two-dimensional form of it for this in Cartesian coordinates, it can be written as dou by dou t of rho phi plus dou by dou x of rho u phi plus dou by dou y of rho v phi equal to gamma, assuming gamma to be constant, dou square phi by dou x square plus dou square phi by dou y square. And we have seen how to discretize this, and especially in the latest example we have seen how this is discretized as part of the simple method for the solution of two-dimensional equations. If we were to discretize this on a simple Cartesian grid of ij, and at point ij we can write this as using forward differencing for this and then backward differencing for the advection term and again backward differencing for the advection term in the y direction, and central differencing for dou square phi by dou x square and central differencing for dou square phi by dou y square here. All these things we can put here and we can rearrange this to get an equation of this particular form. This is our algebraic equation, and in the process we have linearized the u and we have accounted for the the involvement of other equations, the coupling with other equations in terms of v here. And for example, in the x momentum equation we have a source term which is not mentioned here, which is the pressure gradient term. So all those things are done and eventually we have an equation like this, and this can be put in the form of a phi equal to b, where a, phi and b are matrices, or it can also be written as sum over j of aij phi j equal to bi. And since we are summing over j, we are left with I number of equations for the I number of variables. So this is the type of linearized algebraic equation involving these phi's which are the solution variables, for example the velocities at different grid points or the temperature at different grid points, or the u velocity at I plus half j and v velocity at I j plus half, and pressure or pressure correction at ij, temperature at ij, and so on. So the structure of the coefficient matrix A here is important for efficient solution and depends on what type of grid is used. We briefly alluded to a structured grid and unstructured grid. So let's now make a distinction between the two, because we have seen how to discretize on this kind of rectangular grid that we see here, and we have also seen how to do the discretization of a governing equation on a triangular grid. And here we have a slightly more complicated geometry than what we have been dealing with, and you have a wall here and you have a top wall with a converging section, a throat section which is constant width, and then a diverging section here. And for fun we have also put a blockage here which is something like ellipsoidal thing, and we would like to see the velocity profiles as the flow goes over this and then comes out. We would like to find out what is the drag force acting on this, and so all those kind of things we can do. And although we have these kind of angled kind of things and these kind of curved kind of things, it is still possible to put what we call as a structured grid, where a grid point is located at the intersection of coordinate lines like this one here and this one here, and you can see that this is a non-uniform grid here, and you can also see that at this point these coordinate lines are curved. So it is possible to use curvilinear coordinate lines and come up with a structured grid where the grid points are at the intersection of this curvilinear coordinate lines like this, and this particular coordinate line is curving over this part, and then after it goes up here it is almost straight, and this line is like this line is curved like this, but far away from it it is straight. So generation of a body fitted grid, this is known as a body fitted grid with curvilinear coordinate systems, is something that we will see much, we will see in module 6 very briefly. It is not really part of, we are not going to go deeply into that thing, but this is an example of a structured grid. And as opposed to that we have an unstructured grid, and in the case of structured grid, for example, you have this point here and you have a neighbor here and you have a neighbor here, and neighbor, all those things are known. So the neighbors are known by the coordinate line on which they are appearing. For example, for this point here you have an immediate right neighbor is the one which is at the next coordinate line in this direction, and immediate top neighbor is in the next coordinate line in the j direction. Okay. So immediate left is the left neighbor is the immediate coordinate point intersecting the same j line of corresponding to I-1 coordinate line. So in that sense the surrounding, the immediate neighbors information is known here, and each point here has 4 neighbors, 4 immediate neighbors, and maybe 4 corner points and so on in 2D. Whereas here we have a triangulated domain, and the same domain is represented like this, and one could say that at the centroid of each of these triangles is the point where we would like to get the velocities. And you can see that we have small triangles, big triangles, and so on, and if necessary we can put more number of triangles wherever we want, and we can have the velocities determined at the coordinate centers of these grid points. Okay. Now the difference between the structured grid which is at the top and the unstructured grid which is at the bottom is that if you take this point here, the immediate neighbor is here and here and here and maybe here, but for a triangular thing it is only the immediate neighbor who is sharing a face with you matters. So in this sense, if you are starting to put your numbering from here and here 1, 2, 3, 4, 5, 6 like this, then you can see that the neighbors are not somebody whom you know straight away. You need to have some special storage information of who the neighbor is. You cannot say it is I plus 1, I plus 1j, I minus 1j, ij plus 1, all that kind of notation is not possible here. And in this particular case each cell has 3 neighbors, and you could make up a bigger cell here with 4 neighbors or more number of neighbors. So, in that sense the number of neighbors is not fixed in this unstructured grid. But whether you do the discretization on the structured grid or on the unstructured grid, we still end up with an equation like a phi equal to b, which we have seen. Okay. And in the case of structured grid in 2D here, we have for the diffusion equation, for the Laplace or Poisson equation, we will have the 4 immediate neighbors. That is, for point ij we have I plus 1j, ij plus 1, ij minus 1 and I minus 1j. In the case of the Poisson equation on this triangle here, we will have one neighbor here, one neighbor here and one neighbor here. So, this equation will have an equation for this cell will have the value of phi at this centroid, the value of phi at this centroid, the value of phi at this centroid and this centroid. So, it will have 4 variables are involved in this, and in this particular case we will have 5 variables, the point ij itself and the 4 neighboring points. So, in that sense we will have an algebraic equation of this particular form with the corresponding coefficients and with the variables that appear here in for each equation for each cell. Okay. So, in the case of structured grid, the coefficient matrix takes a specific structure. For example, in the case of 2D where you have ij here and ij plus 1, ij minus 1, I minus 1j, ij plus 1, I plus 1j, you have a computational molecule like this. If you put all the unknowns in the lexicographic ordering, then it is possible to get a pentadiagonal matrix which is like this, where you have the main diagonal which is non-zero, usually in the case of delta x and delta y being equal to and if you have, for example, the heat conduction equation or the Poisson equation or the Laplace equation with constant coefficients and so on, this will be -4, 1, 1, 1, 1. So, that is the type of thing that we have for all interior points. So, they all the non-zero points lie along the main diagonal and the immediate higher diagonal and the immediate lower diagonal, and then there will be lots of zeros here, and then you have a non-zero diagonal and then 0 diagonals like this. In the case of 3D where you are looking at a point here and you have an east neighbor capital E, west neighbor capital W, north neighbor capital N, south neighbor capital S, a back neighbor capital B and a front neighbor capital F. You can make up a control volume around this which extends half grid distance in each direction, so that you have a north face here, east face here, south face, west face, front face and back face. Okay. So, on this control volume you can, for example, discretize the governing equation and then end up with a discretized equation which will have 7 non-zero coefficients, and these 7 lie in this form with zeros in between. I think that is not clearly marked here. So, you have the central one, the 2 immediate ones, and then zeros, diagonal, again zeros, a non-zero diagonal, again zeros like this. So, you will have a 7 diagonal matrix, but you have a diagonal structure to the matrix A. This is what you would have with a structured grid. In an unstructured grid, you do not have this diagonal structure, but still the coefficient matrix has certain common features with the structured grid kind of thing, and these common features are important when we consider the solution. And the most distinct common feature of coefficient matrix A is that it is sparse, in the sense that most of the coefficients, most of the constants that appear in the matrix A are 0. Very few of them are non-zero, and how many of them are non-zero? In the general case, that is for an interior point, in case of 3D, for a Laplace or Poisson equation, you will have 7 non-zero values, and in the case of 2D you will have 5 non-zero values. In the case of 1D you will have only 3 non-zero values. So you will have, in the case of 1D, you will have a tridiagonal matrix with these also as 0. Okay. And in the case of general Navier-Stokes equations, you may get more number of points because you may have more derivatives, you have upending and those kind of things. But despite all these things, the number of non-zero coefficients for any cell is far less than the total number of points that are available. So we have what we can call as a compact computational molecule, in the sense that the value of the variable phi at a point is influenced only by a small number of the neighboring cell values, and the influence or the dependence does not go too far into the overall computational domain. So because of this, we will have only a few non-zero components, and therefore the matrix is sparse. So most of them are non-zero, and if you have say 1000 equations, so out of the 1000 equations, each equation will have only about 7 non-zero coefficients. So along each row you have 1000 possible points and only 7 are non-zero, and all the 993 are 0. If you have million grid points, then you have million elements in each row, and out of this million again you have only 7 which are non-zero, and you have whatever million minus 7 is the number of zeros. So in that sense, if you only were to put the non-zero points, it will be like stars in the sky. You will see only some of them which are non-zero and most of them are 0. And so this is a sparseness is a very characteristic feature of a coefficient matrix of A phi equal to B that is obtained from a CFD solution. And as we have seen, it may be structured in the sense that the non-zero coefficients may lie along certain diagonals, and also importantly the coefficients are real, they are not imaginary, because these are essentially the velocities and the properties, some of physical properties of the fluids and the grid spacing and so on. So there is no reason why these coefficients are non-real. So these are real coefficients, and in general the coefficient matrix is very large. For example, a million unknowns, million grid points are something that these days people are doing on their laptops. So that means that if you have million grid points, you have a coefficient matrix has million unknowns. So it will be million by million is the size of this matrix. So we have to deal with these kind of equations in which the coefficient matrix is sparse, may be structured, has real coefficients and is large. Okay. So when you look at this type of A phi equal to B, it is something that is very well known to us, and the one method that has been taught to us from our primary school days or higher secondary school days is the Cramers rule. And if you take an equation like Ax equal to B, Cramers rule says that the solution for x1, x1 is the variable, is obtained by A1 determinant of A1 by determinant of A, and x2 is determinant of A2 by determinant of A, where determinant of A is the determinant of A matrix, the whole matrix A, and A1 matrix is the matrix with the first column of the coefficient matrix A replaced by the vector B, and A2 is for the case where the coefficient, the second column of the coefficient matrix is replaced by vector B, like this. So let us just take a simple 3 by 3 example where you have 3 unknowns phi 1, phi 2, phi 3, and these are such that the 3 equations which give this are 251 plus 352 plus 453 equal to 5, 651 plus 752 plus 853 equal to 9, and 1051 plus 1352 plus 1453 equal to 12. You can see it's a made up kind of thing. And so this equation, as per the Cramers rule, phi 1 is given by, now the coefficient matrix is 2, 3, 4, 6, 7, 8, 10, 13, 14, and out of that, for the phi 1 we replace the first column with the right hand side column 5, 9, 12. So we have 5, 9, 12, and then 3, 4, here 3, 4, 7, 8, 7, 8, 13, 14, 13, 14. So the determinant of this divided by the determinant of the coefficient matrix, which is 2, 3, 4, 6, 7, 8, 10, 13, 14. And you can go through an evaluation of this, the two determinants, and you will get 1.5. If you want to get the solution for phi 2, then it is given by the original members of the coefficient matrix, that is 2, 6, 10 and all that, in which we replace the second column, that is the 3, 7, 13 by 5, 9, 12. So that is why we have 2, 6, 7, 4, 8, 14, these are unchanged, and this matrix, this column here is replaced by the right hand side on 5 and 12 here. Again you evaluate this determinant, and then by dividing by this you get -4. And for phi 3 you take the coefficient matrix, replace the third column by the right hand side column 5, 9, 12. So that is what you have done here. Determinant of this divided by determinant of this will give you the solution here. So in that sense it is pretty straightforward to apply, and it is a very good method in the sense that if there is a unique solution, then you can get it. There is no problem with this method can be applied, and the only condition is that there should be a solution, and you are solving the solutions, you have put together these equations because you feel that there is a solution. If it is a well posed problem, there will be a unique solution. So if you have got a unique solution, Cramers rule will give it to you, but at what cost? Okay. So it can be shown, you can go to many elementary books, you can show that Cramers rule takes n plus 1 factorial number of arithmetic operations for the solution of n equations. Okay. Now what does this actually mean? If you have 10 equations, then n plus 1 factorial is of the order of 4 times 10 to the power 7. It looks like a large number, but these days we have computers which are very fast. For example, you can have a gigaflop personal computer. 1 gigaflop is a machine which can do 10 to the power 9 floating point operations per second. Floating point operations are like this division, arithmetic operations like division and multiplication, and it can do 10 to the power 9, 1 billion of them per second. And here for 10 equations, this method will take about 4 times 10 to the power 7 operations. So that means that you can get to the solution in less than 1.1 second, because you have a machine which can do 10 to the power 9 operations per second, and you need only 10 to the power 7 operations. So you can get that in 0.04 of a second. So it looks pretty simple. Okay, but if you have 20 equations, then 21 factorial is 5 times 10 to the power 19. So if you now have the same gigaflop kind of machine, the time it takes is the number of operations divided by the number of operations it can do per second, which is 10 to the power 9. So that is 5 times 10 to the power 10 seconds. And if you go to 30 equations, the number of operations required will be 8 times 10 to the power 33. And if you divide that by the fastest machine that is available, which can do 30 petaflop operations, so 30 times 10 to the power 15, which is 30,000 times faster than, or 30 billion times faster than your gigaflop machine. Okay. So this machine is 30 million times faster than this, and yet even this would take 10 to the power 18 number of seconds, and that is more than the total age of the earth. Okay. So, that means that if you were to use Cramer's rule and then if you had 30 grid points, then it would take a large number of computational seconds in order to get a solution. Okay. So, 30 grid points is not much, because as part of this course in your first assignment you would have seen that we had grid of 10 by 10, 20 by 20, 30 by 30, that is the number of points. So, for 30 by 30 you would have 900 equations, and here you are looking at only 30 equations. So, Cramer's rule is not something that can be used very effectively because of the number of computations that is required to do the solution, and the killer is finding the determinant. Finding the determinant is really a number crunching operation, and it is not such a good method. Okay. So, we do need to have efficient methods, and here we can see that there are a number of methods, and this is what we are going to explore in the rest of this particular module. For example, if you have a 4 by 4 equation like this, you have 4 equations and 4 unknowns, x1, x2, x3, x4 are the unknowns, and coefficients are constants, and so we have a set of linear algebraic equations which we can write as Ax equal to b, and for the solution of this Ax equal to b we have essentially two types of methods. One is the direct type of methods, direct method for the solution of Ax equal to b, and the other is the class of problems known as the iterative method for the solution of Ax equal to b. Direct methods give solution in a finitely countable number of arithmetic operations and are useful typically for small number of equations. When you have less than about 1000, you can use this, and one such direct method is the Cramer's rule. It gives you in about n plus 1 factorial number of operations, it gives you the solution. The only problem is that n plus 1 factorial is too many operations when we are looking at large number of equations. Otherwise, it is a method which is quite good, it would work, and it is an example of a direct method. Other examples are methods that you might have heard, like the Gaussian elimination method or the tridiagonal matrix algorithm. These are direct methods which will give you a solution in countably finite number of arithmetic operations, pluses and minuses, and mostly what we are interested in from a computational point of view are divisions and multiplications. Iterative methods, on the contrary, on the other hand, are methods which will approach the solution asymptotically. So, you start with some guess solution and then you get an improved solution, you put back the improved solution in this iterative method, you get a more improved solution, and Gauss-Seidel method that we have seen in the first module is an example of an iterative method, and we saw there that with every iteration it was approaching the true solution, and after some 10 or 20 iterations for that simple problem we got a solution which was correct up to so many decimal places. So, that is a characteristic feature of iterative method. You can stop at a certain point when you feel that you have got a sufficiently accurate solution, and if you want more and more accurate solution, you have to go more and more number of iterations. So, to that extent iterative methods never stop. If you want the absolute truth, absolutely correct solution, then you have infinite number of mathematical operations, arithmetic operations. So, we are distinguishing between arithmetic operations and general mathematical operations. Gradient operator is a mathematical operation, whereas here in computer solution that we are looking at for the solution of linear algebraic equations, we are looking at arithmetic operations, that is addition, subtraction, division and multiplication of real numbers. and these are what we are interested in. And usually addition and subtraction take a small fraction of a time required for multiplication and division. So when we look at the number of arithmetic operations that are required for a solution of Ax equal to b, we are usually interested in the number of multiplications or divisions, and it is these things that matter to us in terms of estimating the total computational time. And we have these different classes of methods, and nowadays we have combination methods, and some of the methods that are relevant to CFD, which have gained popularity, which have gained acceptance in CFD, are what we are going to discuss in the rest of the module. So we are going to start with direct methods, and then we are going to some basic iterative methods, and then we will go into more advanced methods in the second week of this particular module. So thank you.